this one. Close that. All right, so second exam, first and the fourth one. Okay, we can do that. So let me open it first and have it downloaded. All right. Okay, so this was the second exam, as intended, and of course it didn't happen because of the fire, the smoke, and then the college, shut down for quite an extended amount of time. So it didn't happen, but I can give you this one as a practice exam for a portion of the final exam, because our scope of the final exam is going to cover what was originally in our second exam and including everything up to, but excluding records or structures. Is that okay? So we're going to take a quick look at this. And, okay, so question number one. Okay, so let me zoom out again. Okay, so this is question number one in the second exam. Okay, projector screen. And the objective of the question is to assess whether... Okay, just miss a few more pixels. Come on, give me. Okay. So the objective of this particular question is to assess whether a person understands the microcode and how the processor works internally. So that is still a part of the scope of the final exam. But let's check out this question and see how we can approach this question and answer that. And let me put on my old person clip-on glasses first. Yeah, that works. At home, I have a full headband kind of hood, so it doesn't put extra weight on my glasses. But I thought that would look even more awkward in the class, so I decided not to use that. Plus, it's harder to transport too. This one is a lot easier. All right. Huh? It's a visor, so it's a... Okay, I can show you what it looks like. Visor Loop. So it looks kind of like this. Yeah. But it's nice in a way because it does not put extra strain on my glasses. So instead it's on my entire head. And I got a pretty big head to support a lot of weight. So this doesn't bother me at all. But it does limit my vision, because I can see the whole class right now, just not everything is in focus. But was that a live translation of what I say? No problem. So this is really handy. I have one for soldering, but the one that I use for soldering is about 2.5x, which has a working distance of 8 inches or so. But it does magnify things a lot, because when I solder surface mount parts, I do need to have that kind of detail. But for looking at the screen, I use a 1.5x, which gives me about 20 inches of working distance. So that's just about right. This has about the same magnification, so it's kind of handy that way. All right, so little distraction. But one of these days, you guys will get to that point too. All right, so getting back to this question. All right, so the question says, assume the following when the first slice of microcode executes. So I give you a particular scenario. The program counter has a value of 27, and all of these are decimal values. So unless I give you a prefix like 0x, which means hexadecimal, or I specifically say it is a binary, or it has a subscript of 2 at the end, which also means binary, everything is by default base 10. Okay? So the program counter has 27, RAM location 27 has content of 125, RAM location 28 has 25, and then RAM location 125 has 27, and so on. And then register A, B, C, and D have values of 33, 161, 0, and 85 respectively. So that's kind of give you the starting condition, the precondition, so to speak. When we first, when we start the first slice of instruction, and then the question continues and says, after each slice of microcode executes, describe any operation performed. So you need to tell me what is going on when that microcode slice executes, and the resulting state of the processor. So if these are the things that I mentioned as a precondition, you have to re-express and go like, did the program counter change? Okay, if not, okay, fine. Did any one of these RAM locations change? Did the register change? But at the same time, if there's something internal to the processor, like the ALU that got changed, or the flag register that got changed, you should mention that as well. So I'm asking you to emulate the processor and tell me what happens when a particular microcode slice executes. Okay? And then the only exception to the rule is the microcode pointer. So note any change, the only exception to the rule is the microcode pointer. So you don't have to tell me, because unless I give you the microcode location of this particular instruction, you can't really tell me what the microcode pointer is going to be. So that's the only exception to that rule. The explanation of what happens in the processor is worth most of the point, and describe the details of what component does what in each slice of the microcode. Okay, so now, what you have to start with would be these two slices. The second column, which is this column here, is the first slice of microcode, and this is the second slice of microcode for the same instruction. So now you have to ask yourself, okay, from here, where do we go? Well, you need that picture of the processor architecture. That is one thing that you absolutely need, because you have to map all of these. And by the way, these names that I use, other than the obvious ones like ROM, other than ROM, they're all using the same name as the tunnels. So if you look up the the processor architecture in Logisim, they have exactly the same names. So let me start it up first. All right, so this is the processor architecture, and I'm going to zoom out just a little bit. This way we get to see the entire thing. And now we have to do side by side, which I cannot do because there's not enough resolution. But what I can do is to put this one on the side just a little bit, so that we can at least see the slice and a portion of the processor at the same time. Okay, so the idea is you have to map out everything, but there are components that are more important than others. Everything that go into a register's enable is important, because if a register is not even enabled, we don't really care what goes into the data port of a register. So you have to prioritize the analysis of a microcode slice like this to help save yourself time in the exam. So the first thing is, okay, PC enable. And you look up PC enable, and PC enable is a 0, which means the program counter is not about to change. If the program counter is not about to change, I don't really care what goes into the program counter. It's not going to change. Is that okay? So you go through this list and find things that are typically non-zero. Okay, I cannot say exclusively that it is only the non-zero terms that are important, but you usually start with the terms that are non-zero, and then you work your way, around that. So if we look down the list, PC enable is 0, program counter mux. It doesn't really matter, because it is only used when you're about to update the program counter. Okay. And then the next one down is address mux. Address mux is only useful when you need to address RAM, when you're using RAM. So we look up here and go like, is RAM being used? No, because RAM cell or RAM select is a 0. So we are not doing anything with RAM, which makes address mux kind of pointless. Okay, it's not going to be useful. You move down the list a little bit. ALU enable is a 1. So that means we are in fact using the arithmetic logic unit. So that's important because that means if I'm using the ALU, then I have to think about what operation am I performing using the ALU. ALUOP specifies what operation. So when you look at this picture here, ALUEN is right here. It goes into the enable of the ALU. ALUOP, or the operation specification, goes into the cell, which is also an input to the ALU. So those are important. So the next question now is, what am I doing in the ALU? So you go into the ALU, okay, assuming you have another piece of paper with only the ALU picture in it. So now the question is, what is operation 4? Well, there's a demultiplexer here. Operation 0, 1, 2, 3, 4. So you follow this line, and that's a bitwise AND. Is that okay? So the bitwise AND operation is what we are trying to do. So the next question now, you can see how, once you know we are using the ALU, then we have all the natural questions of, so what are we ANDing, okay? What is the first operand, what is the second operand, and so on. One of the operands has to come from a register. The other one can be a constant, okay? The first one can only be coming from a register because if you look at in1 of the ALU, it is the output of a demultiplexer, but the demultiplexer has one single input and multiple outputs. So we look at the one input of this demultiplexer, and it's coming out of the register bank. So we know for sure that one of the registers is serving as the input of this AND operation. So now the next question is, which one is it? Okay. So now we go back to the slides here, and the out 0 is selected by RO0 cell, or register output 0 select. So now you look up the given table here, and register output 0 cell is 2. That means register C. Okay, so register C is being used to serve as the first input of the AND operation. Second question, what about the other input? Because bitwise AND requires 2 operands, right? So you track down here and go like, okay, what about the second input? The second input has a multiplexer, which means it can come from 2 sources. One is coming out one of the register bank. The other one is a constant of 0, 1. So we have to kind of know which way it is. To understand which way it is, we look at FC, and FC is the NAND between ALUEN and register output 1 demux. So that means if FC, this pin here, is a 0, it is coming from a register. If it is a 1, then it's a constant of 1. Is that okay? So what about FC? Is the value of FC, the tunnel, is it a 1 or is it a 0? We know ALUEN is a 1 already. So the question now is, what about register output 1 demux? Well, we just look it up here. That's also a 1. 1 and 1 is a 1, but the negation of 1 is a 0. So we know FC as a tunnel is a 0, and that is being used to select the input of this multiplexer. So input 0 is coming in from this particular demultiplexer. The only thing that can feed into this particular demultiplexer is output 1. So we know that the second input to the AND operation is also coming from a register in the register bank. Is that okay? But which one? Well, output 1 is selected by register output 1 select. So we look up this list here, and it is also 2. So we are using register C as both inputs of the bitwise AND operation. Does that sound familiar to you? It should. One of our labs has a question like that. Instead of comparing to 0, we just do a bitwise AND or a bitwise OR, okay? But one is hijacked to do some other operations, and we cannot use that, right? So bitwise AND can. Okay, so when we perform a bitwise AND operation, what is it going to change? What is going to be affected by the bitwise AND operation? The flags, very good. Because, how do we know that? Because we can, okay, so to confirm that, the first thing we need to do is to go into the ALU, And whatever the operation is, okay, it doesn't matter whether it's addition, subtraction, compare, and or bitwise, bitwise not, or shift, they all have to go through this output, right? Which means it doesn't matter what operation we're dealing with, the output is always going to change S out, sign out. It's also always going to change or affect 0 out. So those two flags are always affected by any operation. And they are, okay, so look down here. And then when you look at this, oh, we cannot see that splitter. So when you look at this particular splitter, oops, you can see how the bits are allocated. We got, oh, it's down a little bit more. Huh. You can't see the entire screen that I can, but it's close. Okay, but that's okay. We got this part here. So you can see that sign out is bit 1, and then we can also see that 0 out is bit 1. So those two bits of the flags out port are always affected by any operation that you push through the ALU. Is that okay? All right, so knowing that, we go back to the main portion, and then this time we take a look at the flags register right about this portion. Let me magnify a little bit. There we go. But the flags register, the enable of the flags register is also affected by FC. So if FC is a 1, then the negation of that is going to be a 0, and as a result, the flags register is not going to be updated. What is FC this time again? It's a 0, which means the negation is 1, which means the flag register will get changed. Okay, so the 0 flag is going to get affected by the operation, and then the sign flag is also going to be affected by the operation. Are we doing okay so far with this analysis? Are we storing the result of the operation back to some register in the register bank? That's the next question, because the output of the ALU can store things back into the register bank. Okay, you look at the output of the ALU, and you can see how it kind of wraps around into this multiplexer, and it can potentially be used to update a register in the register bank. But when you look at the microcode slices, you can see that register input enable is a 0. So none of the registers is getting updated in this operation. So register C is going to remain as is, not only because register C and register C is just register C, but also because we are not updating any register in the register bank. Is that okay? So that about sums up the first slice. Okay, I just use words to describe the whole thing, but you can use equations, or you can basically specify what is going on in this operation. Okay, if you just say, okay, this is doing register C, bitwise and register C, it affects the Z flag, it affects the sign flag, that will be fine. I'll take it as a good answer. Is that okay? So it's about doing the same thing as AND CC, except for the fact that it doesn't store anything back to the register, which is actually irrelevant in this case. So now we look at the second slice, okay? So we look at the second slice and go like, okay, what is that doing? So once again, we look at all the important bits first. The program enable bit is important, because if program counter enable is a 1, that means the program counter as a register is about to be updated. Then we have to figure out how is it going to be updated, right? We also look at RAM cell. Okay, RAM cell is a 1 this time, which means we are in fact utilizing RAM for this operation. So now we have a whole bunch of questions to answer. First of all, is it a read operation or is it a write operation? Are we updating RAM, or are we just reading from a location in RAM? That question is answered by RAM load. We are reading, okay? Because when load is a 1, we are reading from RAM. The next question is, who is controlling the address port of RAM? and who's paying attention to the data port of RAM? Those are natural questions to ask once we know RAM is in use. Is that okay? So now we go. So now address mux is important because address mux is helping to decide what is driving or what is determining the address port of RAM. The address port of RAM is this Y over here. This is address mux. So if address mux is a 1, like in this case, then it's selecting input 1, which is coming from the program counter. If address mux is a 0, then it's selecting input 0, which is coming from a particular register in the register bank. Now it becomes important to understand, okay, what is the value of address mux? So we get back to the slides, the microcode slides, and it says address mux is a 1. So it's coming from the program counter. We are using the program counter to specify which location in RAM to read. Is that okay? Okay, now that we know we're reading a location in RAM that is pointed to by the program counter, the next question is, what are we doing with it? So now you have to look at the rest of this stuff here, because PC mux now becomes useful. Because when you look at how the program counter as a register can be updated, PC mux is the key to understand that portion. So let me just scroll the screen to the right part here. Okay, right there. So when you look at the program counter, we know that it's going to be updated because program enable is a 1, but the input of this is selected by this particular multiplexer. This multiplexer is selected by PC mux, but there's no PC mux in the microcode slides because PC mux is not one of the output of the ROM. Okay? PC mux is determined here. Okay? And let me scroll the screen over a little bit. So PC mux is this Y here. Okay, I know we still cannot see the whole thing, but this is PC mux. So PC mux is determined by PC mux, which selects one of the input of this multiplexer to become PC mux. So now the biggest question is, what is PC mux in the second slide of that instruction? So we go back to here, and PC mux is a 1. Okay, so if PC mux is a 1, that means input 1 of this multiplexer becomes PC mux. And this wire goes through here, and it becomes bit 1 of the flags register. That, I think, is the Z flag. So that means we are using the Z flag as PC mux. So now you have two scenarios, because I didn't tell you what well, actually, I did. Okay, I take it back. So now, if you go back to the question, we know what register C is. Register C is a 0. 0 and 0 is 0. And if the result of an operation is 0, what is the Z flag? It's a 1. Okay, very good. So we know as a fact that bit 1 of the flags register is a 1. So we know PC mux is a 1 at this point. Is that okay? So if we know that PC mux is a 1, the rest is fairly easy to determine, because now we just say, okay, PC mux is a 1. We're using input 1 of this multiplexer to update the program counter. And input 1 of this multiplexer comes from another mux, okay? But that's okay, pretty easy to figure this out, because PC mux is a part of this input. This is an AND operation, and PC mux is a 1. Now we need to also look at register output 0 enable, which according to the slides is a 0. So 0 negated is a 1, so we got 1 and 1, which is a 1. So this multiplexer would also select input 1, which is this wire. And if you track down that wire, that turns out to be the data port of RAM. So we are using the content pointed to by the program counter to update the program counter. Is that okay? And that becomes the answer. Okay, PC gets the reference PC. But if you look at that second slice, okay, it is actually the same as the slice for JZI. If you look at just this slice vertically, it is the same as JZI itself. But how can you possibly know that? Yep. Well, the opcode table helps to find the opcode. Then you take the opcode, you pad 10 on the right-hand side, becomes a 3-digit hexadecimal number. You go to that location in ROM, and then you decode that 6-digit hexadecimal number and split it back into all the bits, and you will actually find that, oh, this entire column is really the one slice in JZI as an instruction. But that's kind of what I want you guys to do for studying as far as the architecture itself is concerned. Now, what if you didn't know that? What if I decided, hey, I'm not going to study that? It's still okay. Because if I spell this out entirely, even without knowing that this is the same as JZI, I can work this out backwards, just like what I did. Because what I just presented in the previous 25 minutes or so was not really just to compare this slice with known slices of all the instructions. I just reasoned it out backwards by looking at the tunnels and the meaning of each particular tunnel in the context of the processor. So you can do it in both ways, okay? For those of you who would like to be super ready or super prepared for everything, then you can look at all the slices. I know decoding 25 bits is kind of a hassle, so don't do it by hand. Do it using a tool, okay? Make a little spreadsheet to help you do that, okay? Write a C program to do it. Is that okay? Do we have any other questions about number 1?
So the answer for this one is JC.
The first slice is almost the same as an AND CC. So if you say the first slice is AND CC, but it doesn't store back into register C, I'll count it as correct, 100%. But you still have to indicate the actual result because, I tell you what register C really is. So you have to say, the Z flag is going to be set, the sign flag is going to be cleared. So those are the side effects of the first slice. And then the second slice would be the same as a JZI instruction. But then you have to utilize all of this stuff here to tell me exactly where it's going. Because the program counter is 27, so we're going to take whatever is at location 27, which is 125, and then put it back into the program counter. So the result of executing the second slice of this particular opcode is the program counter ends up with a value of 125. So those would be the answer that I want to see. Is that okay? All right. Are there any questions? So to answer this question, okay, the real key to answer this question is, do we understand this mess? Okay, it looks messy, but once you have looked at this over and over again, it really should not be messy. There are key components here. Do we understand what a multiplexer does? Okay, what does it do? It selects one of the inputs to become the output. Do we know what a demultiplexer does? It's the reverse. We got one input, multiple outputs. The select will help me decide which output is connected to the input. Okay? Do we understand how a register works? Okay, it has got many pins. Okay, the enable pin says, am I ready to update? It needs a rising clock in order to actually do the update. The output is always reflecting the content of the register. The reset, once it is asserted, will zero the content of a register. That's the behavior of a register. So that is kind of what we need to make sure that we understand in order to answer that question. Because now it's just, once you understand how each component works, then it's a matter of mapping out how they connect to each other and how they function as a whole. Is that okay? All right. And then question 4, you said?
Yes.
Okay. So we'll prioritize, and when we have time, we can hit every single question, but we'll prioritize the one that you guys request. first. So we go to question number 4. Now, because question number 1, is presented the way it is right now, so you can almost be guaranteed that it's not going to be like that in the final exam. But it will cover the same kind of topic. In other words, I'm going to have one question to assess whether you understand how the processor works internally. So you will have to understand how the microcode slice affect portions of the processor. Question? I'm thinking about around 5 to 6. I haven't quite decided yet. So one question for sure is going to be microcode, the internal working of the processor and stuff like that. And then one question is going to be like this without subroutines. So I will, not this one here, but the other one, disassemble. There will be at least 2 to 3 questions on subroutines, which can come in several forms. It can be, I give you the C code, you translate into assembly code. It can be, I give you the assembly code, you reverse engineer back to the C code. That sort of stuff. Okay? All right, so this is question number 4 of 4, and the question is asking, when we execute this code, I want to be able to hit the labels, or I want to execute the no ops. I want to hit all the no ops. So I want to hit the no op after C1, the one after O1, the one after S1, the one after Z1, and the one, okay, there should be 5 of those. 1, 2, 3, 4, 5. So each flag, okay, has a label corresponding to it, and there's a no op corresponding to that label. And I want to be able to hit every single one of those. No hands. I think it's probably either a connection issue or the converter, just decides to crap out because it's getting kind of hot. So the good thing is it doesn't affect the recorder. The recorder is still recording just fine. It's just that what you're seeing is not the entire screen that the recorder is recording. So, all right, so we are now back to where we were. Okay, so I want to hit every single one of these no ops if it is possible. Okay, and if you look at the rest of the program, so this means that you still have to understand the rest of the program of how it works. Okay, I load A with bytes, which is a label down there. I load B with bytes end, which is the label of the 1 byte past the end of a whole bunch of byte stuff. Okay, I compare the two. As long as when A equals B, I exit the whole thing. So that will give me to label 4, which is the halt instruction. It ends the entire program. If they do not match, then I will load whatever A is pointing to register B, and then I increment A to the next location, load that one into C, increment A again, and then I'll compare B and C. In other words, what I'm comparing are consecutive bytes after the byte label. Okay, I'll compare one to the other one, but I maintain the pointer, so the next time through this loop, I will be comparing the next 2 bytes, the next 2 bytes, the next 2 bytes. Is that okay? And after I compare, I execute all of these J something I instructions consecutively. Now, you can probably see that it will only take the first one that is true, because this is the same thing as a conditional statement that has multiple branches. When the first condition matches, it will take that branch and then it will forget the rest. Is that making any sense? So that means, if there's a particular scenario where JZI and JOI are both true at the same time, it will take the JZI. It will only go to label Z1, but it won't go to label O1. Is that okay? So that becomes the trick, is how do we get to each one, or as many of these as possible? Is that okay? And the question wants you to fill in these underscores. Okay, the first byte is compared to the second byte. The third byte is compared to the fourth byte, and so on. Okay. So now I'm going to go back to here, and then we'll use a text editor, just a regular notepad thing, to answer that question. Okay. Okay, first of all, I want the 0 flag to be a 1. What kind of comparison will set the Z flag after a subtraction? Pretty easy. Any 2 bytes that have the same value will set the Z flag. Does that make sense? So to do this one, the 2 bytes, only have to have the same value. 0, 0 will work. 0 minus 0 is 0, and 0 will set the Z flag, and we'll go to Z1. Done. What about carry being a 1? If you want the carry to be a 1, then the first number has to be less than the second number in the unsigned interpretation. Well, that's pretty easy to work out too. 0, 1 will do it, because 0 is less than 1 interpreted unsigned. Done. Next one is the sign flag. Now this one you have to be careful, because you can say, oh, using the sign interpretation, 0 minus 1 is -1, and the sign bit of that one is going to be a 1, but that won't work, because 0 minus 1 is already going to label C1 from JCI, is not going to even be tested for sign. Is that okay? Does everybody understand what I'm saying? So now you have to think of a case where the result of the subtraction is still negative, but it is not going to trigger the carry flag to be a 1. So how would you do that? That would do it, right? So -1 minus 0 is -1, and obviously the sign flag is going to be a 1. But why is this not going to trigger the carry flag to be set? Because -1 in using 8-bit is represented as 1111, 1111. The unsigned interpretation of that bit pattern is 255. 255 is not less than 0 unsigned, and as a result, the carry flag is going to be cleared. That gives me the chance to get to the JSI instruction. Is that okay? So that is the tricky part of this question. Is the first one is super easy, because you don't have to consider, oh, I have to make everything false and only this one being true. But as you go further and further down the list, it gets trickier and trickier. Okay, so the next one down is what? Which flag again? The sign flag, the L flag. Okay, so the L flag, I want it to be a 1, but I want every flag before that to be zeros. That is that is the trickiest part. Okay, so I need all the previous ones to be 0. The first one is easy. Okay, as long as the 2 numbers are not the same, the Z flag is going to be cleared. The second one, I need to make sure that in using the unsigned interpretation, the first number is not less than the second number. And yet, using the signed interpretation, it is. Okay. The third one says the sign flag itself has to be a 0 as well. Now that actually gives me a clue of how to narrow the whole thing down. Because in order for the L flag to be a 1, there are only 2 scenarios when we're using sign interpretation. So to understand this part, we have to kind of go back and look at the definition of the L flag. The L flag is the sign flag exclusive OR with the O flag. Right? Okay. So in this case, I want this to be a 1. The sign flag is already known to be a 0, because I need the sign flag to be a 0, otherwise I wouldn't be dropping down to that JLI instruction. So we know that's going to be a 0. So now the question is, 0 exclusive or what is going to be a 1? What do you think? What is the definition of exclusive OR? Different from is the one way to look at it. So I need the overflow to be a 1. Okay. So now we have locked down the overflow has to be a 1. Then the next question is, knowing overflow is going to be a 1, What does that imply? So now you have to pull the equation of the overflow flag. Let's say that you completely forgot to include that piece of information in the little cheat sheet that you want, but you have the processor architecture with you because you knew that I'll be asking about the processor architecture, right? So what do you answer? How do you answer this question? How do you go back in time and go like, oh, what is the equation to compute overflow from all the other flags? This is how you do it. You go to the ALU wiring diagram, and then you scroll down until you get to this part. This mess here is computing the overflow for subtraction. So now you just look at these gates and go back, oh, okay. So in order for the overflow, which is this wire, to be a 1, I can have this one being a 1, I can have this one being a 1. This is just a regular OR, it's not exclusive OR. Okay, what else do we know at this point? What do we know about the sign of the result of the operation? We need it to be a 0, right? Because otherwise the JSI is going to branch, and I wouldn't be able to get to the JLI. Is that okay? So that means S out is going to be a 0. If S out is a 0, this is my only chance. Because this one says, let's see, oh no. Because this one says, S out is just fed directly into an AND gate. Well, this is an AND gate. If S out is a 0, the output is automatically a 0 of the top AND gate. The bottom AND gate, on the other hand, gives me a chance. But if the output of the bottom AND gate is to be a 1, S out is not a problem because we know it has to be a 0. We also know that the minnow has to be negative, and then the subtrahend has to be non-negative. Is that okay? Are you guys still following me?
How can you know that S1 is
Because if S1 is not negative, then it would be a 0 here, and if any input of an AND gate is a 0, the output is going to be a 0. But we want that output to be a 1. Okay? Is that okay? So this is constraint-based reasoning. Okay? We want a particular desirable outcome. So now we have certain restrictions. And if the top AND gate is out of the question, there's no way the top AND gate can do what we want it to do, because we already know the sign after the comparison, after the subtraction, has to be clear. It has to be a 0. Okay? So now we have basically locked down what the minuend and subtrahend has to be. The minuend has to have the sign bit being a 1, and then the minuend needs to have the sign bit being a 0. And then we have to cause an overflow. So you start with a negative number, you subtract a positive number from that negative number, and it overflow the representation of an 8-bit signed integer. That is what we're looking for. Okay, so once we know that is what we're looking for, working it out is actually really easy. You start with the most negative value you can start with, you can have, which is negative 128. And then you just say, I'm going to subtract 1 from it. And that would meet this requirement. Is it? 128 minus 1. Yeah, that would meet the requirement. Are we okay so far? Okay, let me write down the answer first, and then I'll let you guys ask questions about it. Okay? So in order for this to happen, the first number has to be negative 128. Negative 128, if you write down negative 128, I'll count it as correct. Okay? And then the second number has to cause the overflow. Well, 1 is enough, because negative 129 cannot be represented as an 8-bit signed integer. So that's going to cause the number to overflow, right? Think about the bit representation, okay? Think about binary numbers. 128 is represented by what? 1 followed by 7 zeros, right? What happens when you subtract 1 from 1 followed by 7 zeros? Just look at the binary perspective, not the decimal perspective. It becomes 0, and then 7 ones, right? But that's 127. Well, that's exactly why it works, because it's overflowing. Is that okay? So we are now down to the last one, but these all kind of relate back to the processor architecture. Because even if I do not remember the definition of the overflow flag, the architecture spells it out for me. Did you guys see how I went into the ALU schematic diagram and used that to help me answer this question? So that's where you kind of have to think about, okay, the processor architecture actually tells you everything about how it works, how the processor works. So if the instruction is asking you, or the question is asking you something specific about the internal operation of the processor, somewhere in the processor architecture is going to help you. All right, so we're down to the last one. This one is super duper tricky because I need everything. I need Z, C, S, L to be all zeros. But I want O to be a 1. It turns out to be impossible. But then you have to explain to me why it is not possible. Okay? So how would you explain to me why this is not possible? Okay, in order for O to be a 1, I got 2 chances to do it. I can have, okay, so now we need to refer to the minuend sign, okay? The minuend sign being positive, and then the subtrahend sign being okay, minuend sign is negative, is a 1, so minuend itself is negative. And then the slash here, okay, let's use the exclamation point because that's easier for negation. And then the sign of the subtrahend is going to be cleared, so we're dealing with a negative value minus a positive value. And then the result, which is our sign flag here, has to be non-negative, okay? So SS is the sign of the subtrahend. S itself is the sign of the result. That's one chance, one way to make it happen. And I kind of need it this way too, because if the sign flag of the result is a 1, I would have taken the JSI and done, okay? So I have to take this one. But at the same time, okay, so this is one restriction I have to deal with. But at the same time, I have to look at the the L flag. The L flag is a 0. Can someone remind me again how we define the L flag? In terms of the other flags? O. Okay, that's an O. But we know overflow needs to be a 1 because that's what we are looking for, right? So we know the L flag is whatever the sign flag is exclusive with a 1 in this case. So what does it tell me about the sign flag? It has to be a 0. Okay. So this implies the sign flag needs to be a 0. Okay. Which is consistent with this particular case. So now we have to look into the case where the sign of the minuend is negative, and then the sign of the minuend is a 1, the sign of the subtrahend is a 0, which is resembling what we already have seen here. And that would have been, yes. We're looking for, okay, so the L flag, by definition, is the sign flag or exclusive or with the overflow flag. That part you can actually look up the processor architecture in the ALU. It spells it out in gates, okay? But we already know we want overflow to be a 1 because we want to take the JOI branch, right? So overflow has to be a 1, so we know the overflow is a 1. But in order for the something exclusive of 1 to be a 0, oh, wait. Oh, we want it to be a 0, so the sign flag needs to be a 1 now. Okay, I take it back. Okay, that was my goof up here. This needs to be a 0. A 1, sorry, yeah. So the sign has to be a 1 in order for the L flag to be a 0. But now we have a conflicting thing, right? Because I want the sign flag to be a 1, to be a 0 here, but we also want the sign flag to be a 1 here. So just because of the constraints of where we are at this point, we have a conflict, we have a contradiction. And that's why it is not possible. That would be the explanation of there's no way we can take the JOI branch at this point because it is the fifth one. Is that okay? So that's kind of how I would answer that question. But it's once again it's constraint-based reasoning. Okay, you're trying to use whatever clue, whatever information that is supplied to you in the question to place constraints on what you can do. So you're working within the constraints to solve the problem. Some of you are smiling.
I was wondering if we take this test,
Mm-hmm.
how many of us can answer this question?
I don't know. You're asking me about an event in time that has not occurred.
Who can answer this question?
I think but there's partial credit. Okay, most people can work out the first three for sure. The fourth one, some people can, and let's say the last one is the trickiest, and most people cannot. Well, they still get 60 to 80% of the score of this question, which in my books is a high C, low B, all the way to B, right, middle of a B, which is not bad. Is that okay? But there's nothing new in the sense of we have not talked about any of the material that is needed to answer this question. The only thing that is new that I haven't really talked about is problem solving skill. That is the only part that is missing, the missing piece to answer this question. But I don't know how to teach problem solving skills. That's difficult for me to explain. I try my best to. This is my explanation. Okay, trust me. I did not have the answer memorized in my head coming into this class. I read the question and then I reasoned out, the question, just as you guys are reasoning out the question. So you were in the past, 20 minutes, you were listening to a internal dialogue in my head of reasoning out this entire thing. And that's the best I can do to teach how to reason things out. Yep. Um, you can, but the question is, do we have answers for those solutions to those exams? Because I keep every single final exam that I have ever given. Some I might have lost, over time, but in the past few semesters, like recent semesters, I have those. This is the other thing you can do. You can go to the share folder. The shared folder actually has a lot of resources. So when you go to the shared folder, and you go to old FX, all the old final exams, or some of them can be found here. Some is not relevant anymore because I have changed the architecture since then. So some of those questions assume that you were working with the older architecture where some of the features were still missing, and we're trying to figure out how to add the features that are currently already in the architecture. So that's why I don't want to touch those questions because it might lead to more confusion. Since your scope also includes exam 2, I also keep track of some of the old exam 2 questions. But once again, exam 2 also touches the architecture, so some of the questions or some of the answers of those questions do not apply anymore. Because the instructions like JMPI, JCI, those are all kind of newer instructions. Before that, we only had JC, JMP without the I. which means your jumps look a lot more cumbersome with that. And now that we have JCI and JSI and JLI, things look a lot cleaner. Sorry? These have what? No, I don't think so. I don't think some of those features were in 2016. Yep. I can tell you what I'm testing. What I'm trying to assess is whether you guys understand how the processor works internally. How do you know how to translate C code into assembly code? Do you understand how to translate assembly code back into C code? And just in general, can you keep track of the registers to understand, oh, we're accessing this parameter, and now we're accessing this local variable, and then we're accessing that parameter again? And are we getting the address of the parameter? Are we getting the value of the parameter? Or are we getting what the parameter is pointing to? Those are the concepts that I'm really assess and see if you understand those particular concepts. So to study for the exam is really, first of all, you have to understand the C code very clearly, okay? So, okay, give you a solid example, okay? All right, so I'm just gonna continue with this note here, just gonna move on, so this way it's not confusing. Okay, so the question is, if I give you, void f, okay, the function itself doesn't really matter, but here's a local variable, okay, uint8 underscore t x. Do you know how to get to this? Do you know how to get to this? And if this is a pointer, okay, do you know how to get to that? That is the question. How do you know how to differentiate between the three, going in one direction, going from C code to assembly code, and then going backwards, looking at the assembly code, understand whether a block of assembly code is giving you the address of a local variable, the value of a local variable, as opposed to what the local variable is pointing to. So that means you have to really brush up your C first, and then relate that to assembly code. Yep, go ahead. Say again.
So in this case, it would be the stack pointer, is the address of that?
Yes, because it is the only local variable, it will be the stack pointer. But then you have to kind of think about what happens if this is sandwiched between two local variables. So, what if I have another uint8 underscore t, and this time making an array of 5 elements, and then over here we have another local variable, a whole bunch of them, 2 of them. So now it's not nicely, it's not the last one anymore. So now, can you get back to it? Stack pointer, add 2 to the stack pointer, correct. Yep. Because, okay, so in this scenario, okay, if you look at the assembly code in F, okay, if I want, the address of X, and I want to put it into a register, this doesn't work, okay? So let's say we're dealing with register C, that does not work. It does not compile, okay? So anyone giving me code like this is telling me that, that person does not understand the opcodes, does not understand the mnemonics, and also the supported operation of an opcode. So that will be points deducted. Because what you can put on into the immediate side of an LDI instruction or JMPI or whatever I instruction the value has to be determined at assemble time. The assembler has to be able to resolve the right-hand side and say, oh, this resolves to this particular value. This is not resolvable at assemble time because it depends on the runtime value of the stack pointer, which changes all the time. Right? So this cannot, it's not okay. It doesn't work. So the only way to do this, well, not the only way, but one way to do it is to do a CPR, okay? CD, we copy register D to register C, and then you increment C twice. Okay, that works. If you define the labels accordingly, in other words, if you define x as a symbol that is defined to be the number of bytes from where the stack pointer points to where you can find x on the stack, it is just an offset, then the other way to do it is to load cx, load immediate cx, and then add cd. That will work as well. Because if you define the label x correctly, it would be 2, right? So we are basically copying 2 to register C. So register C now has a value of 2. And then we add the value of the stack pointer, whatever it is at the time we execute that opcode, to 2. So that means, it is just whatever the stack pointer is plus 2. So both blocks of code would accomplish this. It's just that one makes use of the newer feature, having you can define labels any way you want using the postfix notation, and then the other one does not use that feature. Okay, you first, and then you. Yep, go ahead. Uh huh.
What if you change the stack pointer as you're going?
Then you have to adjust for it. Yeah, then you have to adjust for it. So, okay, I'll push your question on my stack first, and then I'll look at what your question is.
Before line 38, you would initialize the label x.
Nope, it's assuming x is already initialized. Okay, so if you make use of labels, then you have to choose how you want to define the labels. So according to the last time I looked at the C compiler, register, so in this case, whatever is declared last has the lowest address. So Z is declared last, so it's pushed or allocated last. So Z would define to be 0. Y is going to be 1 byte on top of Z because it's the second last local variable to declare, so it will be Z1 plus. And then X is going to be the one on top of that, so Z is going to be Y1 plus. And then array A is going to be 1 byte on top of X, so it's going to be X1 plus. So these labels have to be defined first before you can utilize the label X. So if you choose to use this route, then you have to define the labels first. Now, if you say, I don't like postfix notation and I can do this math in my head and I'll just define Y to be 1, X to be 2, A to be 3, that's fine, not a problem. Okay, you do not have to use the relative mode of defining those labels. So I'm popping the question back from the stack, but of course my stack is corrupted. What was the question again? Yes, okay, gotcha. Okay, so let's say we're using the second approach, okay? And we encounter something like this, okay? We call another function g, okay, whatever it does, doesn't matter. And we want to push the address of x as the first argument, and then we have a constant of 23 as my second argument, okay? So that will demonstrate this idea. So in order to perform this call, okay, I'm just thinking about where to put this code so that everything still remains on screen. This particular mouse pad doesn't give me the ability to split the screen, so I can look at one portion and scroll through the other portion. But I think we get enough room here. Okay, so to implement the call to G, we will have to push 23 first. So we have a LDI A23, decrement D, ST, D, A. So this, just push 23 as the second argument. So now we have one more thing on the stack. The stack pointer is no longer pointing to, the offsets are off by 1, okay? So now the question is, how do I get back to the address of X? Well, it's going to be about the same thing. You do LDI, C, or A, whatever register you want to use, X. But now you say 1 plus, okay? Then you do a add AD. Now register A is the address of X. We can now push it as if it is just, a usual thing. STDA. Yep.
Change what again?
No, because label can only be defined once. You cannot redefine a label as you go. So that becomes an issue because you cannot redefine the label. So z, once you define it to be a 0, it has to remain as a 0. So that's why you cannot adjust everything relative to it. Yep. So there's no quick and easy way to do it. This you pretty much have to mentally keep track of what is on the stack and whether you have to add a particular constant because you just pushed something on the stack and the labels are now off. Okay? This is typically what a compiler has to do too. So I'm just turning you guys into organic compilers. Well, the array is, remember what A is? A as a label in assembly is really a symbolic name that defines the number of bytes that is between where the stack pointer points to and the first byte of whatever A is. Now, in this case, A is an array of 5 elements, okay? But does it really change where it starts? It doesn't.
So what is the array you haven't defined?
Well, I don't even need that, okay? So if f takes arguments, okay? So let's say it has one argument, union8 underscore t, p1, okay? So if I want to define p1 using this particular scheme, then p1, okay, first of all, we have return address. Don't forget the return address is the last thing pushed by the caller, okay? So it's going to be A5 plus because A as an array takes up 5 bytes. Okay? And now P1, which is parameter 1, is going to be return address 1 plus. So the best way to do this, when you're trying to answer questions and stuff like that, or when you're reviewing material, is to draw a picture. Okay? So when you draw a picture, you have to think about it from the perspective of the caller first. Okay? What does the caller have to do to call f in this case? It has to push all the parameters. Last parameter first. Well, we only got one, so we take up 1 byte for P1 as a parameter. The caller also has to push the return address. Next byte down, okay, this is high memory address, this is low memory address. So the next byte is used by the return address. Then we start to allocate local variables in the order that we see them in the C code. So the first thing we see is on line 24, we are declaring an array of 5 bytes, okay? So 1, 2, 3, 4, 5 bytes. This is collectively local variable A, which is an array. Then we see X, okay? Then we see Y, and this is where Z is. So this is the order of the allocation. The last thing that you allocate is where the stack pointer is going to be pointing at. So register D, after doing all the allocation, is going to be pointing to local variable Z. So when you look at the offset of each thing away from where the stack pointer is pointing to, Z is being pointed to by register D right away, okay? So the offset is going to be a 0. Y is 1 byte away, X is 2 bytes away, A is only 3 bytes away because we're looking at the first byte of the construct. A has 5 bytes, but the address of A only refers to the address of the first of the 5 bytes. Is that okay? What about the return address? Well, 4, 5, 6, 7, 8, okay? And then P1 is 9 bytes away from where the stack pointer is pointing to. But the problem is, if you are calling another subroutine, like on line 31, we're calling G, then you have 23 pushed here. Then the stack pointer is no longer pointing here, and everything is now 1 off. And as a result, in assembly code, we have to adjust for that 1 plus by, okay, if I can just kind of scroll down here. So we have to adjust for that 1 additional byte that you have just pushed on the stack on line 51 by saying it's not just x, it is x plus 1. Is that okay? So pictures, usually help. The problem with the picture is every picture is only a snapshot of what the stack would look like at a particular time. As you execute instructions, incrementing D, decrementing D, putting stuff into D, and so on, that picture is going to change. So it will take you a little bit of time to draw pictures on the instruction by instruction, or at least a key instructions to understand how the stack or how this stuff changes over time.
So the P1 has the address of 255?
I don't know. I don't care. Because I don't know, who is, calling F. If it's main calling F, maybe. It also depends on whether main itself has local variables or not. So everything floats with the stack pointer. That is the most important part that you have to remember, is you don't really want to tie in these locations to absolute locations in RAM.
So what if it is called column? So
What if,
so what if the it's called it is a main function. So
okay.
the address will be P1 will be 255 or
Well, but main can have local variables, which would use up some locations on the stack already. So that's why, you don't want to think about it this way. When you look at a subroutine, only look at the memory look at the memory, how should I put it? Look at the frame, the layout of memory from the perspective of where is everything relative to where the stack pointer is pointing to. That is what you need to think about when you look at a subroutine. But do not think of it as, well, if the caller, is calling me when the stack pointer is at this location, these are the absolute locations, because that is not going to help you, when you're thinking about more complex subroutines. Does everybody understand what I mean by that? Everything with a subroutine is only relative to where the stack pointer points to. So when you draw a map like this, okay, the key is, well, the stack pointer is pointing here. Where do I find everything else? Map it out. Is that okay? Is it helping? Cool. So you might want to bring additional sheets of paper, okay, in the exam, because if you want to doodle and draw the maps and stuff like that, you might need more space than it is provided in the exam itself. And if you want to turn in your scratch work, including all the pictures and whatnot, you can do that. Okay, I don't mind, when I look at your answer, in addition to what I'm looking for, there's a whole bunch of pictures. Doesn't mind. I don't mind that at all. Is that okay? So one thing you can do to prepare for the test is to go through some of the programs that I have written in class and have verified to be working, like the swap subroutine, the Fibonacci program, that's what the Fibonacci subroutine, and give yourself a particular case, okay? And one thing you can also do to kind of study for this test is to put in the program that I have written, like swap or Fibonacci and stuff like that, run it through and collect the trace, okay? I would trace the program counter, the stack pointer minimum, okay? And then the last few locations in RAM, okay? If you want to, also track down all the registers, okay? Registers A, B, and C, because it's not really that many more items. So trace the whole thing, okay? And then try to explain line by line, row by row in the trace, what is that row representing? What is happening? Which opcode executes and what is actually happening when it executes. It sounds really tedious, right? But that's how you study for this class, is to make sure that you understand the operation of the whole thing. Alternatively, you can also just kind of flip a coin, roll a random number, go to one particular row and go like, okay, what is that row representing? How is it different from the row before? And why is it different from the row before? That works too. because the program counter will tell you what opcode is corresponding to that row in the trace, and the row before that row will tell you what is the precondition, what is the memory layout, what are the values of the registers, the stack pointer right before that happens. So you just have to kind of explain, why is that row the next row? Is that okay? If you want to even go further to understand loops, control structures, and stuff like that, then you also want to log the flags register, because the flags register is affected by compare instructions and a bunch of other instructions. That is why we make branches, conditional branches. So by logging the flags register along with everything else that I just mentioned, then you can actually see, oh, at the very beginning of this while loop, we have just gone through the last iteration. The flag is now becoming 0, and so the the Z flag becomes a 1, and that's why we branch out of the loop. You can actually see that, from a trace. So I would use the trace, as a way to help you understand the programs that we have talked about in this class. Is that okay? It helps to study together too, even though you guys cannot work on the final questions at the together during the final, and still have the points count. But it does help to kind of study together, so that so that you can share your results. Like someone is going to enter the Fibonacci program and collect the trace of f of 3. Another person can enter the swap program and collect the trace when you're exchanging two particular values. So one person doesn't have to do all the things, okay? And then you can share the trace and analyze the trace together, and make sure that you guys can exchange ideas and make sure the understanding is consistent. So that may work. All right. I don't know exactly what else to recommend as far as studying goes. I'm the kind of person who don't study. Studying doesn't help me when I was in college. Having a good night's sleep. No, I'm serious, because I absorb the material during class and when I work on the homework assignments, and then as I go along in the semester, I make sure that every single concept that I encounter is crystal clear in my head. So by the end of a semester, I have all of that stuff in my head already, and if it's not open book, open notes, then I have certain things to memorize, like symbols and mnemonics in this case and whatnot. But otherwise, the understanding, the framework is already here. I just need to memorize notations and stuff like that. So that's the only thing I usually study for, would be the notations and things that I need to memorize. So is that okay? We all think and process stuff differently, so the way I study and prepare for an exam may not work for you. So you have to find out what works best for you. I can only give you guys suggestions and alternatives. Is that okay? All right, yep.
In question 3 of exam 2, you used the RSH mnemonic. Was that a mnemonic they used previously?
It's in the table. So I assumed you guys, would bring, all the resources that are available to the class in the class with you. So RSH is right shift. It is in the opcode table. So, yeah.
So here's a $1 million question.
I don't have $1 million.
What features of processor carry over to real-world processors?
The principle in general, the fact that we have registers, and the registers have pathways to connect to the ALU. The ALU affects the flags register. The flags register in return can affect conditional branch instructions, and how registers can connect to the address port of RAM. So you can use a register to specify which location to look at, and how the data port connects back into the input of the register bank, so you can update a register based on a particular address in RAM. So all of those are relevant because every single real world processor has those features. So that is how it is relevant to a real world processor. Mm-hmm. The toy processor, if anything, is just the much more simplistic version of a real life processor. So that's a good question. Unfortunately, I didn't have time today to go over a hacking example. I got it all prepared, but I didn't get to do it. It's based on the understanding of assembly code, even though you may not understand the AMD instruction set, but by understanding what the stack is used for, what is a return address, and how conditional statements are structured, I would be able to demonstrate it so that you guys go like, oh, okay, so if I understand assembly language programming, how C code relates to assembly programming, I can actually hack a program. I can reverse engineer things to make a program do something it's not supposed to. Yep.
So I know that sometimes when people write like C or C++,
Uh-huh.
I've heard that you can embed assembly.
Yes. So
Post an example
it is a little bit complex. I can show you where you can look for more information. The recorder is still on, so you can actually read this part here. So GCC has inline assembly code. The use of inline assembly code typically is only when there are certain things you can't really do in C, like really low-level stuff. Then you have to drop down to assembly stuff. But it will still be in the context of a C subroutine, so you cannot break out of a subroutine and just say, I want to write something random in assembly code. You still have to contain that assembly code, the inline assembly, within the context of a subroutine. Yeah, but if you want to look into inline assembly code in C code, that's what you're looking for. Yep. All right, we have to clear the classroom because the next class is coming in. I'll be over at the lab in case anyone wants to ask questions. And for those of you who want to watch how I hacked that program, you can watch the video of the Monday, Wednesday class because I did it yesterday. So the video from yesterday actually has that.